Okay, so far in this class, we've been doing some measurements on properties of matter like mass and volume, but sometimes properties of matter are a combination of different measurements that we would usually make separately, like density. So we can figure out how massive something is, how much matter is packed into something by using something like a digital balance, a digital scale. We can figure out volume by using length times width times height for a block. We can use different volume calculations, or we can use a graduated cylinder or other glassware to measure out the volume of liquids and things like that. But density requires both mass and volume together to kind of calculate to get a number on it. Now, density does have kind of a like a sense about it. You can kind of tell just by picking something up and by your experiences say, oh, this feels a little bit heavier than I would expect, or lighter, or about what I would expect. Okay, so density by definition is how much matter you have packed into a certain amount of space. Okay, if something feels heavier than it maybe should be, that means you're packing in more matter than you would expect. Okay, typically things like metals are like this, where we have big heavy atoms that are crunched in together real close, and they are packed very efficiently, like a suitcase when you're going on vacation. There aren't a whole lot of gaps. There's a very ordered structure to it, kind of like playing Tetris. Something with lower density typically has lighter atoms that have more gaps, that have more spaces in between, a more open structure where things aren't packed as efficiently. Okay. In either case, if you can kind of feel out whether something seems pretty dense or not so dense, whether something is more or less dense than another, in science, we want data. We want to have a number on something to tell us exactly how dense something is. So we use the mass and volume to do that. Okay, the density is essentially just the mass in grams divided by the volume in milliliters. If you go and look up densities online of different materials, you might find other ways to measure it. Because as long as it's mass and volume, it works out the same way. But typically in chemistry, we use grams for mass and we use volume as milliliters. Now you could also do cubic centimeters, like cc's or cm, 3 exponent to the power of 3. But for this lab, we're just going to be looking at milliliters, and we can cover cubic centimeters and stuff later. Okay, so if I have a mass in grams and a volume in milliliters, and I divide that mass by that volume, that grams divided by milliliters, that gives me a ratio of mass to volume. How much mass do I pack into how much space? Okay, that result is the density, and it's measured in grams per milliliter, kind of like miles per hour. Okay, how many miles do you travel in an hour? How many grams can I fit in a milliliter for this substance? Okay, so in the lab, we're going to be doing just that. We're going to measure the mass, which is something that we're pretty familiar with. We're going to measure volume, which is something we've also done before, but in this case, we've got to put a spin on it. We've got to get a little creative with how we measure the volume.
I've got a sample of nickel here, and I want to figure out the density of this little nickel marble here. So in order to calculate the density, I need the mass and the volume of this thing. The mass is the easy part. I've got a mass balance right here. And if I set it carefully on here, I might be able to get it to stay. Yeah, there we go. It reads out 15.0 grams. So there's 15.0 grams of matter in this nickel marble. So I've got that. Next comes the volume, which is something I have to get a little clever with. Now, if we had a nice block-shaped object, we could do length times width times height in centimeters times centimeters times centimeters. That would give us cubic centimeters, and then that would be a volume, which we've done before with a block. In this case, I've got a marble. Now there is an equation for the volume of a sphere that I could try and use. And the metal samples we're going to use in the lab are cylinders. Also, there is an equation for that volume, but a lot of these have imperfections. They have markings and divots, rounded edges. And in this case, the nickel ball is not a perfect sphere. You can see kind of there's some like flat dented edges, just how I got it to kind of stay on the mass balance so nicely. So if I want to get a better measurement of the volume, something I might do is use a graduated cylinder like this. Now, graduated cylinders are great for measuring the volume of liquids in milliliters, where the big lines go up by 5, so 10, 15, 20, and each little line goes up by 1, so 25, 26, 27, 28, 29, 30, and so on. Now, this nickel marble is not a liquid, but I can show how much volume it pushes out of the way of a liquid if I put the liquid in first, look at where I start, add the marble, and then see how much that liquid level rises. Okay, so I'm just going to use water because it's available and cheap as my liquid, and it's not going to do anything to the nickel marble here. It's not going to react with it or anything like that. Okay, I just have to be careful as I put the nickel marble in. Since this is metal and this is glass, I don't just want to dunk it, or else I'm going to bust the bottom out of this thing, which has happened before. So you just have to kind of be careful. So we're going to kind of tilt it and slide it. So I am starting at about 31 milliliters. I'm going to drop in my marble very carefully and see how that water level rises. So I'm going to tip my graduated cylinder a little bit, drop it in there. Oh, I got a little bubble there. Okay. And my water level is now at, let's see, 30, 31, 32. Not quite. Looks like about 32.5. So if my water level raised by 1.5 milliliters when I threw in that marble, then that is the volume of the marble. So I've got my volume of just the water, I've got the volume of the water plus the marble. If I subtract those out and remove the volume of the water itself, all I'm left with is the volume of the marble, or my metal sample, however it's going to be. So that's going to turn out to be about 1.5 milliliters. Now, if I've got the volume in milliliters and I've got the mass in grams of my nickel sample, then I can calculate the density, which is just the mass divided by the volume. Experimentally, I determined the mass to be 15 grams. I determined the volume to be 1.5 milliliters, so I've just got to divide out 15 grams by 1.5 milliliters. So if you run this through a calculator, or you got some good mental math, our density of this nickel sample is going to be 10.0 grams per milliliter. Now, this is what we determine in the lab, but it doesn't necessarily mean that it's absolutely correct. So we would have to go compare it to a known value where someone has done research over and over and over to determine the density of nickel. And we compare it to that value we find in published research or literature or things like that. In this case, the actual density of nickel is 8.9 grams per milliliter. So just kind of comparing them. Not too bad. It's not perfect though. If I want to know just how close or how off I am, we can use something called the percent error to calculate kind of how close I got, or better yet, how far off I was. The equation looks something like this. So I want to find the difference between the experimental value I determined in lab and that so-called actual correct value that I can look up, in a published resource or online, things like that. Okay. Once I have that subtracted, I've got that answer, I divide it out by the actual density, and then finally I multiply by 100. Now, a couple hints or tips to kind of help you out. These bars on either side here, let's see, there and there, are absolute value bars. And essentially, they're just going to wipe the negative sign off of here if you get one. If you get a negative number, that's nothing to freak out about. The negative or positive just tells you whether you are above or below what you expected. So if my density is above what the actual true value is, then I'll probably come out with a positive number. If I'm below, it's going to come out with a negative. That's all it means. But typically, we also just absolute value it, so the negative goes away, and we don't have to worry about it We just see how far off we were. We don't care whether we were above or below. Okay. Now, also, if you're using a fancy calculator, like a scientific calculator, if you type all this in at once, so you take, 10 minus 8.9 divided by 8.9, your calculator is probably going to do order of operations for you and divide the 8.9 by 8.9 first before it does any subtraction, which is not what we want. We want the experimental and actual subtraction part to be its own separate step. Okay, so make sure you either use parentheses in your calculator or you do that top part first, get an answer, and then divide it. Okay, once we multiply by 100, that changes us from a decimal to a percent, and that tells us how far off we were. Once I plug in my experimental and my actual values, I take 10 minus 8.9, then divided by 8.9 times by 100, and I get 12.36. So I was about 12.36% off of what I expected, which for this lab is not too bad. Just because we try really hard doesn't necessarily mean we're going to get accurate results. Some of it depends on the instruments that we use, like the graduated cylinder. It's only split between every 1 milliliter, so we can only get so good with our eyes to distinguish between a 0.1 and a 0.2 and things like that. And the mass balance is pretty good for us. Okay, so there's my percent error there. So this is pretty much what we're going to do for our lab, except with 5 different metals. We're going to do it for lead, copper, zinc, aluminum, and tin, each marked with a little letter or a symbol so that you can tell them apart.
All right. This lab is in the Unit 1 folder. We're still in Unit 1 here. So if I open this up, we're looking at Unit 1, Lab number 2, Density, Part 1. Part 2 is going to be a separate thing. So Unit 1, Lab number 2, Density, Part 1 is what we're looking for. If I click on this, I will be taken to this page here where I've got my PDF for my lab. This is what I'm going to open with Cami so I can write in my data and do my calculations. We've also got Unit 1 Lab 2's presentation, so the slides I was just kind of showing and what I'll use in another video here. So if you want to go back to those and look at them for notes, that's there. Then I've also got this video linked that is, it's a funny little representation of how mass and density can get confused. Highly recommend it. It's real quick, like just a little over a minute. So if you haven't seen it, definitely check it out. Okay, so I'm going to open this with Cami here. And here I've got my lab. So I've got some instructions up here at the top. And I've got some places where I'm going to be taking some data like mass, change in water's volume, experimental density, actual density is given to me, and the percent error, where the equation for percent error is down here at the bottom. So I can work that out here. So I'll be plugging in values for mass and the volume of 5 different metals: lead, copper, zinc, aluminum, and tin. I'll be using the mass and the volume to calculate the density, since density is mass divided by volume. Come on, purple here. Where to go? There we go. Density is mass divided by volume. All right, this is my mass. This is my volume. Okay, and I can compare that to the actual density of that material. I can figure out exactly how off I was using this percent error here and my experimental density. Again, calculation is down here.